All right, let's jump right into this explainer. Today, we're going to unpack the fascinating geometry, physics, and machining processes needed to create the ultimate kitchen cutting tool. Specifically, we're looking at the incredible engineering behind a full, flat, double-bevel kitchen knife, taken all the way to a razor-sharp edge. Now, it might just look like a standard piece of sharp metal sitting on your cutting board, but I promise you, there is an absolute mountain of science behind every single slice.
Here's a quick look at our blueprint for today's explainer. We'll be hitting 1. The physics of cutting, 2. The full flat grind, 3. Double bevel edge engineering, 4. Machining the perfect bevel, and finally, 5. Achieving a razor edge. Let's get to it.
Section 1. The physics of cutting. Understanding the wedge. To really understand how a knife works, we first have to look at the foundational physics of what a blade actually does when it meets material. At its most basic, fundamental level, a knife is just a simple machine. It's a wedge that concentrates force into an incredibly small area, creating high pressure to literally push matter apart. But before we head to the grinder to make our own, we need to answer a seemingly simple but absolutely crucial question about that geometry. What exactly is a bevel? If you go pick up any knife in your kitchen right now and look at it edge on, you'll notice the steel isn't just completely flat all the way down. At a certain point, the metal starts to angle inward.
Well, that angled surface right there, that's the bevel. Think of it kind of like the slope of a roof. A steep roof sheds snow super quickly, right? In the exact same way, a steep bevel creates a really thin, acute edge that slices through food with barely any resistance. On the flip side, a more gradual slope leaves a lot more metal behind the edge. Sure, it's way sturdier, but it definitely won't cut nearly as cleanly. Those specific angles and shapes dictate entirely how a knife performs.
Moving on to Section 2. The full flat grind, minimizing drag.
It's actually wild, but research shows that a blade's grind geometry affects cutting performance way more than the actual steel type itself. By tapering in a perfectly straight, consistent line from the absolute top of the blade, which we call the spine, all the way down to the cutting edge, the full flat grind gives us the thinnest possible wedge for a given piece of steel. It creates this beautiful, really long V shape when you look at it in cross-section.
So why does this matter so much? Well, this flat geometry absolutely excels at general daily tasks because it gets rid of the excess material that normally causes a blade to bind or get totally stuck in deep cuts. It just effortlessly parts cardboard, food, packaging, you name it. You're getting minimal drag when you're slicing into dense root vegetables or, say, a giant block of cheese. This is exactly why it's a huge favorite for both everyday carry and high-end kitchen knives.
Section 3. Double bevel edge engineering, tracking, and symmetry. If we zoom right in on the very bottom of the blade, we can contrast these two choices to highlight exactly why a double bevel is the gold standard for home cooks and chefs alike. A double bevel has its edge ground symmetrically on both sides. Because it's pushing food apart equally on the left and the right, it tracks in a perfectly straight vertical line. Now compare that to a single bevel, which is ground on only one side. That creates an asymmetric wedge. It pushes food to one side while the flat side glides along the cut. That's amazing if you want paper-thin sushi slices. But if you're just trying to chop an onion, it causes the blade to steer diagonally right into the food. Not ideal. Now let's talk numbers, specifically the exact angles of that double bevel. Japanese-style double bevel knives are typically ground down to an incredibly sharp 12 to 16 degrees per side. This super narrow angle gives you an exceptional cutting feel with dramatically less resistance. I mean, it literally glides through proteins and vegetables like they're butter. By comparison, your typical Western kitchen knives usually sit at a much wider 20 to 22 degrees per side. Now, this sacrifices a little bit of that extreme laser-like thinness, but you gain greater durability against chipping. That's great if you're occasionally hitting a bone or doing some heavy rock chopping on a cutting board, but for pure slicing joy, that 12 to 16 degree Japanese double bevel is absolutely the sweet spot.
All right, Section 4. Machining the perfect bevel, from steel to tool.
So we've got our geometry blueprint down perfectly. Now we need to translate that to a piece of raw steel. While freehand grinding is an incredible art form, using an adjustable grinding jig provides the consistency, precision, and frankly the safety needed to flawlessly machine our engineered angle. A jig securely holds the blade right against the abrasive belt grinder, completely removing the guesswork so we can get that perfect full flat double bevel. The actual physical procedure starts by scribing a center line straight down the edge of the steel blank so you know exactly where the middle is at all times. From there, you make steady, incredibly smooth passes on the grinder. If you hesitate for even a second in the middle of a pass, you'll create a wobble in your grind line. And here's the kicker. It is absolutely vital to stop grinding when you still have about 1 to 2 millimeters of edge left. You do not grind to a sharp edge yet. Why? Actually, you have to leave that little bit of extra material to keep the thin steel from cracking or warping during the extreme high heat of the heat treatment process that comes next.
And this is a super important point. Maintaining a consistent bevel is entirely about locking in your body mechanics. As expert knife maker Walter Sorrells puts it, if you use your wrist to move the blade, the angle is going to change, and you'll completely ruin the flat grind. Instead, you have to lock your elbows tight to your sides and use your entire torso to sway the blade across the grinder's platen.
Now, when you transition the grind near the handle, an area we call the plunge line, you have to carefully rock and feather your pressure to prevent the abrasive belt from digging in. If you press too hard instantly, the belt will literally take a chunk out of your steel, and your perfectly straight grind line is completely ruined. It's all about smooth, feathered pressure right there.
Finally, Section 5. Achieving a razor edge, the microscience.
Okay, so after heat treating to harden the steel and doing some final finning on the grinder, we transition to the very last step. It's really important to understand this distinction. Grinding and sharpening are absolutely not the same thing. We've finished the heavy grinding to create our full, flat primary bevel. Now we're dealing with microscopic edge refinement. Sharpening is really just about realigning and smoothing the very apex of the edge without removing much material at all.
This brings us to the science of abrasives, which completely dictates our grit progression. Grit numbers just refer to the number of holes per square inch in the mesh they use to sort the abrasive particles. So we start from a coarse grit in the low hundreds to raise a burr, move up to a medium grit to refine the edge, and finally step up into the thousands for a beautifully polished, surgical edge. So the actual sharpening process means carefully working your way through these abrasive steps on a whetstone or a fine belt system. You start on one side until you feel a tiny microscopic lip of metal roll over to the other side. That's what we call the burr. Once you feel it, you switch sides. You have to pay extremely strict attention here to perfectly match that original 12 to 16 degree angle we machined earlier. If you change the angle now, you'll compromise literally all of our hard work. Ultimately, this level of micro-refinement, it's totally up to you. If you stop at a 600 or 1,000 grit, you get a toothy working edge. Those microscopic serrations basically act like a fine saw, aggressively biting into slick things like tomato skins or heavy rope. But if you progress to a 6,000 grit or even higher, you erase those teeth completely, achieving the absolute smooth perfection required by a sushi chef for delicate, mirror-smooth cuts. Which brings me to a question I'll leave you with today. If a blade's geometry actually dictates its performance more than the steel itself, how much potential is hiding right now inside the dull knives sitting in your kitchen block? We learned today that it's the full, flat grind in that perfectly angled 12 to 16 degree double bevel that makes a knife truly sing. Hopefully this explainer has given you a newfound respect for the intense engineering, physics, and geometry that goes into your daily cutting tools. Next time you slice an onion, just think about the incredible science happening right at your fingertips.